The purpose of today's current balance lab is to find the magnetic field strength of a particular horseshoe magnet. You guys know what a horseshoe magnet is, right? It's a magnet that is shaped like a U, or more like a horseshoe, with a north pole and a south pole. We want to find the magnetic field strength of this horseshoe magnet. Now, let me tell you how we're going to do that. There's two parts to this experiment. In the first part, we're going to change the strength of the electric current flowing through a wire, measure the magnetic force, and from that find the magnetic field strength. In the second part of the experiment, we're going to change the length of wire in the magnetic field, see how the force responds to that, and then determine the magnetic field strength from that. So in two parts, both of which you're going to find the magnetic field strength, and then you're going to combine them, which I'll show you how to do that when we get to the end of this. Here's what your apparatus is going to look like. You see a power supply right here. This is what's acting essentially as my battery, although this power supply allows me to change the electric current, so I'm not stuck with a specific potential difference or a specific electric current. You can see it's hooked up via wires to this thing over here that we call a current balance. This current balance is attached to a retort stand that we see in chemistry. Now, attached to the end of this current balance is a printed circuit. This printed circuit, you guys know what a printed circuit is? We see printed circuits in electronics all the time, in computers all the time. Basically what it amounts to is wires, and sometimes other components as well, although in this case only wires, that's built right into a little circuit board. It's printed onto a circuit board as opposed to having like a separate wire that we took off of a roll or took off of a spool. So we have a printed circuit here that has this wire attached to it. That little printed circuit that we see right here is able to be plugged into and unplugged from the current balance. You'll see that when you walk into the lab here in just a couple minutes. Now this printed circuit is placed in between the poles of a horseshoe magnet. Make sure that when you put it in there that you don't have the printed circuit touching the magnet anywhere, but make sure that the entire thing is within the magnetic field, so in between the poles of that horseshoe magnet. Finally, you see that this is all on a scale. Scales measure mass, right? There's the apparatus. This is what this thing is going to look like. Now, what exactly are we going to do to collect our data? Well, the first thing you're going to do is place the wire, I call it the wire here, but really it's that printed circuit, in the center of the magnetic field. Try to make it as parallel to the magnets as you can, which makes it perpendicular to the magnetic field. Make sure it doesn't touch the magnet on either side or on the bottom. Make sure that when you do that, the scale reads 0. You will likely have to press the tare button or the 0 button in order to make that happen. Does that make sense? So it should read 0 now. If it's not reading 0, then press the 0 button to trick it into thinking there's no mass on this. Now, on the power supply, you're going to turn the voltage knob as far to the right as possible, as far to the right as it will go. You will turn the current knob as far to the left as it will go. And you should see a reading of 0 here and 0 here. Then you're going to turn up the current knob a little bit. When you turn up the current knob, there's going to be a current reading on that power supply. So no longer is it going to read 0. It's going to read 0.15 or 0.23 or whatever the case may be. Read the value of the current and read whatever the scale says as a result of that current. How come the scale is reading something? How come it says 0.29 grams now and it said 0 before? This thing isn't any heavier, right? The mass is the mass. This scale doesn't actually measure mass. This scale measures weight, and then it gets electronically converted to mass. Basically, this calculates mass from weight. It's calibrated to gravity of 9.81 or whatever gravity is here. But here's the thing. if you push down on that scale, it tricks it into thinking there's more mass there. There's not. There's just more weight there because you're pushing down on it. When I apply a current through this printed circuit, when it's exposed to this magnetic field, there will be a magnetic force on the wire. But by Newton's third law, if the magnet applies a force on the wire will apply an equal and opposite force on the magnet. So it pushes the magnet down, tricking the scale into thinking there's more mass. Does that make sense? Now, one little thing here that's not a huge deal, but you see the way that I have this set up with the red side of the magnet on the left side and the white side on the right side. Set it up that way. Okay? That way you're going to get a positive mass there. If you happen to switch it around and left is white and right is red, it's not the end of the world, but if you do that, understand that you're going to get a negative value for mass because the wire will be pulling up on the magnets instead of pushing down. That's not a big deal. Okay, if that's what you get, either switch the magnet around or just drop the negative sign. Either way works just fine. What you don't want to write down as your data is a negative value for mass. All right, so this is what your data table looks like, or at least your first one. Write down the length of the wire. That's going to remain constant. Doesn't really matter what that length is. But I would suggest, just because you see the effect more if you do this, I would suggest using the longest wire. And the longest wire is 8.4 centimeters. If you forget that, it's not a big deal. It's just that it's a little bit harder to notice the effect if you use a shorter wire. Okay, record your current, your first current, and then your first, notice I put mass in quotation marks here because it's not really mass, right? It's what the scale thinks is mass. Change the current to a higher value, okay, write down the new mass, and so on, 10 times. What you want to do is make sure that the current, though, remains under 2 amps. If you happen to slip a little bit above, it's not the end of the world. You're not going to get electrocuted. You're not even going to get hurt. You're not even going to feel a shock unless you go way over. But as a matter of good habit, okay, we're going to set a maximum value and stay under that maximum value. Now, just so you understand, 2 amps is a lot of current. 2 amps in some situations can be deadly. It will not be deadly here. You will not even feel a shock if you touch a bare wire here. But 2 amps, given sufficient potential difference or sufficient voltage, is enough to kill you. So, next month you're doing something and some electrical thing and you remember from class, oh, we used 2 amps that day in class. I'm fine using 2 amps here. Not necessarily. Okay, so just remember that 2 amps isn't always 2 amps, if you know what I mean. Sometimes it's safe, sometimes it's not. Today it is. Next time, maybe it's not, depending upon the context of it. All right, so don't go over 2 amps. Part 2. Remember, in part 1, we kept the length of wire constant, changed the current. In part 2, we're going to keep the current constant and change the length of wire. Your current should be held at a constant value of approximately 1 amp. It's a little bit above, a little bit below. It's okay. It's not a big deal. Okay, if sometimes it's hard to get it to an exact value, 1.02 amps is just fine. Just make sure you keep it at that current. In this experiment, you're not going to touch either the voltage knob or the current knob. They're going to stay where they are the whole time. You can see it's set up the same way. But this time, this time, instead of changing the current, you're going to change the length of wire by subbing in these different little cartridges that have the printed circuits on them. All these different lengths of wire. Okay, record the constant current that you're using, 1 amp, 1.02 amps, whatever it happens to be. Record the wire length and then the so-called mass that goes with it, and then repeat that 6 times. Anybody know why we're only doing 6 trials for this? Because we only have 6 cartridges for different lengths of wire. Okay, so 10 for the first one, 6 for the second one. What do you think you're going to do next? Create some new tables, some analysis tables. You can see from experiment number 1, this is really just your data. But we've created a new column here for magnetic force. How do you think we're going to find the magnetic force? No. Graphic's coming, but not yet. We're not going to use ILB. Remember, this scale has been tricked into thinking there's more mass. Really, it's not more mass, it's extra weight. So the magnetic force is really just the mass, not real mass, but what the scale thinks is mass, times 9.81, m times g. Make sure you convert that mass to kilograms before you do that calculation, but once you do, you simply got to multiply by 9.81, and you've got the magnetic force. Do not use F is equal to ILB for this. Okay, use F is equal to m times g. Same deal over here. But make sure, again, that mass is in kilograms. Now, we're going to plot a couple graphs. Magnetic force versus current for the first experiment. It will give me a straight line. And from that straight line, you're going to do your y equals mx plus b thing to determine the value of the magnetic field. Then, you're going to plot a graph for the second experiment, force versus wire length. You're going to do your y equals mx plus b thing to once again determine the magnetic field strength. What should you find? What should you find when you calculate these two magnetic fields, experiment 1 and experiment 2? They should be the same. It's the same magnet, right? That's a control variable. Although you don't need to list the variables, that would be a control variable, the most important control variable. It should be the same. It may not be exact. It should be close. Once you've calculated both of those, find the average magnetic field between the two, and then conclude the magnetic field strength is blank, and this is known because. Give me a brief explanation as to how you determined what that magnetic field is. Give me 2 or 3 good sources of error as well, plus suggestions for improvement. So what do you got to hand in for this? Your data, no procedure, no problem, no materials, none of that stuff. I just want to see your data, which is your table, actually 2 tables. Your analysis, which is 2 more tables, except these ones have 3 columns, and your 2 graphs. Your conclusion, which is what is the value of B and how do you know? And then your sources of error, 2 or 3 good sources of error, plus your suggestions for improvement.